I just thought I'd do a quick video about the link between the migration that arises from diffusion, and then also the migration that comes about through conductivity, and this allows us to link together diffusion and conductivity. So that's why you learn all about conductivity and measuring the conductance of a solution and everything, and that's why you measure diffusion constants and diffusion layer thicknesses and everything. And when we link these two together, we can get a really good understanding of each other. So often what you'll do is you'll measure some sort of conductivity measure, and that will allow you to deduce what the diffusion constant is, and also the diffusion layer thickness. So the big thing to note is that in all of this, the reason why things will migrate is so that the chemical potential there's some sort of gradient in the chemical potential. Okay, so there's a lower place that the system could be in chemically, a lower energy state that the solution can be in. And it's just like osmosis, where you have a migration of ions across a membrane in order to lower the overall chemical potential. And so the chemical potential, as we saw earlier, which is just Gibbs free energy divided by number of molecules, is equal to some sort of mu naught, and then you've got this term that considers the activities. But what we're adding now is a electric field component. And so this component here will talk about the diffusion, or some sort of gradient in terms of the concentration gradient, because remember, activity is kind of a way of thinking about concentration. And then this here will be looking at migration, which originates from some sort of electric field. And then this here is from this will be some sort of diffusion. And so that's one thing we can calculate. The second thing we will do, so we want to kind of work out the speed at which things kind of move through the solution. And so we'll just say that speed is equal to is then proportional to the gradient of the chemical potential with distance. Okay, so if I've got a solution here and a solution here, and this has a higher potential than that, then there'll be a movement of ions between those two solutions. Okay, and the constant of proportionality is going to be just some sort of frictional constant. So this is a placeholder, and we're going to calculate what this is later. Okay, so this is going to be an equation for speed, and so it's going to be the gradient of the chemical potential. So let's do that. Let's look at the gradient of this. And so if we go, S is then equal to negative F. Oh, sorry, that's actually negative F. D mu dx. So it's negative F, and then we're going to collapse that all in. And so if we take the derivative of this with respect to x, then RT is not going to change, but there will be a change there could be a change in the activities as a function of distance. I'll just delete this here. And then there will also be potentially a gradient in the electric field. So the number of charges shouldn't change. This is a constant, but there could be a change in the potential as a function of distance. Okay, so we're thinking about, is there an electric field set up between these two regions? Is there a higher concentration in this region than another region? And so this is where diffusion comes in place. If you're making molecules at an electrode surface, they have to diffuse into the solution, and then once they're in solution, there must be some sort of electromigration. And so this talks about the electromigration, and this considers the change in that concentration gradient. So we can consider two cases, And the two cases will allow us to derive two different equations that we can then equate at the end to calculate some sort of link between these two. So the first case we're going to consider is when the only thing that's going on is pure electromigration, and so there is no change in the activity or the concentration as a function of distance. So nothing's being created here, nothing's being absorbed, and so the only thing that's going on is the movement of ions in the solution. Okay. I'll just pause there.